Hello everyone, my name is Antoine Thomas and on behalf of Seisnetics team I will introduce today a new artificial intelligence using a genetic algorithm which is used to extract and reveal more features from any 3D seismic volume. And the demonstration will be done on a public dataset from offshore the Netherlands called the F3 block. So after a quick introduction, I will give an overview on how the algorithm works and the additional insights it delivers compared to other existing methods. And then I will discuss its application to the F3 block dataset using a short video to provide an idea of the full potential of the method. So the success of any project dealing with the subsurface requires a good understanding of the latter, whatever it is. So gas storage, oil and gas production, geothermal, CCS. Then with the wealth of seismic data available, AI can be seen as an enabler to process these vast libraries, which, by the way, are often sitting on shelves or hard drives. And the idea is to build better and more accurate models of the subsurface. And today, the vast majority of machine learning approaches are supervised, which means they require an initial training to help them achieve the desired goal. But this training, of course, introduces a bias. So eventually the final results will depend on the initial human touch and interpretation which was input as a starting point. And on the contrary, our focus today is on an unsupervised, fully automated pre-interpretation processing AI, which uses a genetic algorithm to deliver extremely fast, independent, and unbiased examination of all the data from 3D seismic volumes or libraries. So how the algorithm works. So basically the volume is automatically segmented and organized into waveforms, which we can consider equivalent to genes. These waveforms throughout the volume start to join together into populations, referred to as geopopulations here, based on their genetic and spatial compatibility. Each population of waveforms has a common waveform, which we call genotype, which continually evolves as new trace waveforms are added to the population. So the evolution of these populations continues and continues until a minimum fitness threshold is reached for all geopopulations and all horizons or every peak and trough is extracted from the volume. So for each population extracted, it's possible to display 3 attributes, including amplitude, the Z-maps, and fitness. And so you see here a fitness map, so it's an horizon, top view. And the fitness is an attribute unique to Seisnetics. It maps the morphology of the seismic waveform in response to changing reflector geometries. And so on a picture representing a geopopulation extracted from the F3 dataset, you can first see a range of colors from green to red, which displays how much the waveform encountered along the section differs from the genotype. So you have the genotype at the bottom left, and you have a cross-section, and every time you encounter a waveform, you have a color. So in green, all the waveforms encountered have characteristics very close to the genotype, while in red, they differ more significantly. It's like if you want the first cousin and second order cousin from blue to red. And so this form of seismic facies mapping can be visualized as a surface or a volume and brings a new level of geological details when you combine, of course, with other data such as well data. So now let's see how we apply this AI to the F3 block dataset, which is located in the Dutch sector of the North Sea. And you will see there are a number of interesting features that we can observe in this package, including large sigmoidal bedding and bright spots caused by gas pockets. And so I decided just to play a little video that might be more efficient to describe how it works. So here what you see is the software itself, and you have the seismic, one seismic inline which is displayed, and you can, of course, go through the volume, play a little video to see how everything evolves and changes along the different inlines. And here is a window of the geopopulation display. So every horizon or geopopulation which has been extracted. I have selected all of them, and now I will display the results of the extraction from the algorithm. So this is what you get after here less than 8 minutes of processing. So you have every peak and trough which can be displayed directly on the seismic. So you see all the horizons, and then you can select any of them to go through the details. And you can also change the view to display the fitness. So once again, green is close to the genotype, and red and blue, you see some differences. And so here with this kind of video, it's called what we call the quick look. And you can spot the outliers, and you can help the interpreter focus on what changes to have the global picture, but then get very fast into the details. And as you will see here, you will see some very interesting features coming here. Which is something like a break in the fitness, which appears in red and purple. And so then the idea is to select one of these horizons and to see what they are and what's happening there. And so I switch this in 3D to provide a view of this horizon slash geopopulation in 3D. And then I go to the fitness map of this horizon into the viewer. And you can see some very nice features well delineated with the fitness attributes. I can narrow down the range of the color range, the raster range, to only display the waveforms which are very close to the genotype. And you see that then this number decreases and decreases as you change the color range. And of course, the question is, what are these features? So you can then display the amplitude, change the color, put a different color scale, and then analyze what you see. And you see here that you have a very bright spots, so very large amplitude contrast, 10 times more than the average. And basically these are gas pockets, gas accumulation, which you have been able to display. You can see that we have computed a fault and that the gas accumulation on the southeast is bordered by a fault. And that's an example of a quick analysis of the results. Another one here in the geopopulation, which is somewhere a bit deeper into the seismic. I want to provide you with another example on how the fitness can help provide more geological details. So here you start to see patterns, direction, northwest to southeast. You can see when you narrow down that there are some features which look like channels on the left, maybe riddles on the right. You can display the amplitude, you can display the depth map on that case and other attributes. But let's focus on the fitness. And the beauty of Seisnetics here is, since you have a genotype, you can process parts only of the waveform. So here, for example, this horizon is associated with to a peak, but I can process some parts above or inside the horizon. And you see, for example, if I process the top, I see some very nice channel features with a green facies. We don't know what it is, but we can guess what it is from now, even without well data. And I can try to see how this evolves with the verticality through the waveform. We see that we still see the channel, and if I process the lower part of this waveform, then basically the channel disappears. So this processing approach can help go below the seismic resolution. We can process down to 8 milliseconds intervals, and you can really see the change, geological change of features along the intervals to really provide insights into, for example, seal or reservoir characteristics, the evolution of facies and the verticality. And one last example, also a bit deeper in the seismic. You see already on this horizon that you have some strange circled features which are displayed with a lower fitness. It means they are in the same family but way further away from the genotype. And so when you change a little bit, again, the raster range, you clearly see them delineated, and you can even see changes inside. And so when you know these data sets, you understand these are carbonate mounds. And you see how amazingly they pop up into this horizon, and how we can analyze very fast what's happening in any horizon which has been extracted. So this is it for the short video. And for the conclusion, then I would like to say that this is a new unguided and unbiased tool that really can help interpreters focus on what matters, like you see the outliers or specific zones, but also keeping a view on the whole volume. This is very fast, so these results and what I have shown you today has been done in 4 minutes. It took longer to shoot this video, basically. And so you can really cut the time spent on picking horizons. And you also have access to a new level of geological details revealed by the AI that can be calibrated and correlated with whale data, petrophysics, for example, to understand what the color ranges in the fitness are representing in terms of geology. And another application that is not discussed here is, of course, since you can very fast extract horizons, you can use this tool in PSD and PSDM workflows to improve velocity models, images, and decrease the time spent picking. And with this, I would like to thank everyone for their attention, the SCG for the workshop, and we'd be very happy to answer any question. Thank you.